Hello and welcome back to Steven Data. Today in this video I am going to talk about the Poisson distribution and its properties like mean and variance. But before diving into its details, please subscribe to this channel if you are interested in data science, statistics and machine learning. Okay, now let's get to it without further talking. A widely used distribution emerges from the concept that events occur randomly in an interval, or more generally, in a region. The random variable of interest is the count of events that occur within the interval. But before diving into the details, consider the following example. Flaws occur at random along the length of a thin copper wire. Let x denote the random variable that counts the number of flaws in a length of t millimeters of wire, and suppose that the average number of flaws per millimeter is lambda. We expect the expected value of x to be lambda times t from the definition of lambda. The probability distribution of x is determined as follows. Partition the length of wire into n subintervals of a small length of delta t, which is equal to t over n. If the subintervals are chosen small enough, the probability that more than one flaw occurs in a subinterval is negligible. Furthermore, we can interpret the assumption that flaws occur at random to imply that every subinterval has the same probability of containing a flaw, say p. Also, the occurrence of a flaw in a subinterval is assumed to be independent of flaws in other subintervals. Then, we can model the distribution of x as approximately a binomial random variable. Each subinterval generates a flaw or not. Therefore, the expected value of x equals lambda times t or n times p. And one can solve for p to obtain p equals lambda times t over n. From the approximate binomial distribution, our probability mass function equals n choose x times p to the power of x times 1 minus p to the power of n minus x. With the small enough subintervals, n is large and p is small. Basic properties of limits can be used to show that as n increases, the expression n choose x times lambda times t over n all to the power of x is equal to e to the power of minus lambda times t. Therefore, the limit of the probability mass function as n goes to infinity equals e to the power of minus lambda times t times lambda times t all to the power of x over x factorial. Because the number of subintervals tends to infinity, the range of x can equal any non-negative integer. The recent example can be generalized to include a broad array of random experiments. The interval that was partitioned was the length of a wire. However, the same reasoning can be applied to an interval of time, an area, or a volume. For example, counts of particles of contamination in semiconductor manufacturing, flaws in rolls of textiles, calls to a telephone exchange, power outages, and atomic particles emitted from a specimen have all been successfully modeled by the probability mass function in the following definition. In general, consider subintervals of a small length of delta t and assumes that as delta t tends to 0, first, the probability of more than one event in a subinterval tends to 0. Second, the probability of one event in a subinterval tends to lambda times delta t. And third, the event in each subinterval is independent for other subintervals. A random experiment with these properties is called a Poisson process. These assumptions imply that the subintervals can be thought of as approximate independent Bernoulli trials with the number of trials equal to t over delta t and success probability of lambda times delta t. And all of these lead to the following result. The random variable x that equals the number of events in a Poisson process is a Poisson random variable with parameters lambda that is greater than 0, and its probability mass function is equal to e to the power of minus lambda times t times lambda times t to the power of x over x factorial. And it's interesting to know that the distribution is named after its developer, Simeon Denis Poisson. The parameter lambda is the mean number of events per unit length. It's important to use consistent units for lambda and t. For example, if lambda is 2.3 flows per millimeter, then t should be expressed in millimeters. Now, let's see an example. For the case of the thin copper wire, suppose that the number of flaws follows a Poisson distribution with a mean of 2.3 flaws per millimeter. What is the probability of 10 flaws in 5 millimeters of the wire? Let x denote the number of flaws in 5 millimeters of wire. Then x has a Poisson distribution with lambda times t equals 2.3 flaws per millimeter times 5 millimeters, and that is equal to 11.5 flaws. Now, if we plug in the number into our formula, we will have the probability of x equals 10 equal to e to the power of minus 11.5 times 11.5 to the power of 10 over 10 factorial, and that is equal to 0.113. Now, what is the probability of at least one flaw in 2 millimeters of wire? Let x denote the number of flaws in 2 millimeters of wire. Then x has a Poisson distribution with lambda times t equal to 2.3 flaws per millimeter times 2 millimeters, and that is equal to 4.6 flaws. Therefore, the probability of x is greater than or equal to 1 is equal to 1 minus the probability of x equals 0, and that is 0.9899. Now, as always, let's see what the mean and the variance of the Poisson distribution are. If x is a Poisson random variable over an interval of length t with parameters lambda, then the expected value and the variance of x are both equal to lambda times t. Yes, it's a little bit strange, but the mean and the variance of a Poisson random variable are equal, and I will prove it to you why in later videos. But now, imagine if particle counts follow a Poisson distribution with a mean of 25 particles per square centimeter, the variance is also 25, and the standard deviation of the counts is 5 per square centimeter. Consequently, information on the variability is very easily obtained. Conversely, if the variance of count data is much greater than the mean of the same data, the Poisson distribution is not a good model for the distribution of the random variable. Now, it's time to wrap up the video by reviewing what we have learned so far. First, we saw that the Poisson distribution is a discrete probability distribution. It gives the probability of an event happening a certain number of times within a given interval of time or space. Then we saw its probability mass function, which was equal to e to the power of minus lambda times t times lambda times t all to the power of x over x factorial. And then we saw its mean and variance, which both were equal to lambda. And that is done. Congratulations! Now you know what the Poisson distribution is, and you can solve and model real-world problems with its help. And remember, for more information about other distributions, you can check out this playlist. Finally, if you like this video, please hit that like button, and if you are interested in statistics, data science and machine learning, please consider subscribing to this channel. By the way, if you have a question about the fields I mentioned, comment it down in the comment section, and don't forget to share my videos with your interested friends. I hope this video helped you a lot, and until the next video, happy learning!